So far, we've learned about how charges interact with each other. Charges create electric fields. Electric fields exert forces on charges. And so if you place two charges near each other, each one experiences the electric field created by the other. And those fields, in turn, generate forces on our charges. Now, if a field can exert a force on a charge, that means a field can do work on a charge. And if a field can do work on something, then it implies that there is a transfer of energy. And if there's a transfer of energy, it means the fields can store energy somehow, and that's what we're going to talk about today. Before we start talking about electric fields and energy, let's take a step back and let's think about the energy associated with gravity, because gravity is also a field in the same sense that electric fields are, and they have a lot of the same properties. Imagine that we're close to the surface of the Earth, where the gravitational field is more or less constant, where these uniformly spaced gravitational field lines represent a field, G, which is equal to 9.81 meters per second squared downwards. Consider an object with a mass m0 held at a height r above the ground. We would say that this system has potential energy because if this mass were released, it would fall under the effects of gravity, speeding up, and it would gain kinetic energy that it didn't used to have. That energy has to come from somewhere, and that's what we call potential energy. Since we said that the ground is what we're going to call h equals 0, we would say that once it reaches the ground, it has no more potential energy. It's fallen to the ground, it can't fall anymore, and so it has lost at least some of the potential energy that it had. If I consider the two different configurations, one where our object is sitting on the ground, and another where our object is back at height r, the configuration where the mass at the top has higher potential energy, and the configuration where the mass is at the ground has lower potential energy. If we again start at the configuration where the mass is at a height r, and we release the mass, it will fall under the influence of gravity, which is to say that it will experience a force of gravity as it displaces downwards. If we think back to what we learned about energy, then since the force of gravity points downwards and the object experiences a displacement that's also downwards, then the force of gravity does positive work on the mass. And since we set it up so that the object started at a height r and then at a height 0, the total vertical displacement had a magnitude of r. Since the gravitational force did positive work on our mass, that means there was a transfer of energy from the gravitational field into the mass. We lost some of the potential energy of our system. So gravity doing positive work, the potential energy of the system had to go down by the same amount. In other words, if our field does positive work on something, it means it's using up some of the energy stored in the field, which means its potential energy is going to decrease. If our field does negative work on something, for example, if I took my mass and I lifted it back up, that means energy is being put back into the field, and so it's gaining potential energy from some external source. I'd like to consider essentially the same exact situation, except using electric fields instead of gravitational fields. Once again, we want to deal with a uniform electric field, just like we had a uniform gravitational field over here. And one way that we could accomplish this in practice is if we set this whole thing up inside of a parallel plate capacitor where the top plate is positively charged and the bottom plate is negatively charged. Taking the charge on our object to be positive, how much work would the electric force experienced by this charge do in bringing it from the positive charges to the negative charges? Since the charge is positive, it's going to experience a force in the same direction as the electric field. And just like before, it will experience a downwards displacement. So far, this looks essentially identical to the case on the left with gravity, and that's because it really is. It's just a different kind of field, but it's doing exactly the same thing. So once again, let's actually calculate what the work done by the electric field is. We have the same exact setup this time as on the left. This time, it's just instead of having a mass m0 and a force Fg, we have a charge q0 and a force Fe. And so if we write down the work done by the electric field, that's equal to the electric field dot product with the displacement. And as we can see, this is more or less the same, except the electric force is Q naught times the electric field instead of mg, and the displacement is still r. And once again, this is positive because the field, or the force, and the displacement are in the same direction. Now, a really good question to ask at this point is, where did this energy come from? Well, it was an electric force that pushed the charge. That's the force that did the work. And so there was a transfer of energy through this electric force. And so that energy had to come from the electric field, since that's what generated the force in the first place. In other words, there is some kind of energy associated with the field that is simply present. It depends on where all the charges are, and it can be used up or added to depending on the forces on the charges in the system. Well, that's just potential energy. And so we can talk about the change in potential energy of this system. And again, since the field or the force did positive work on our charge, that means energy was added to our charge. For example, if it was freely moving through this field, it would be getting faster and faster and faster, gaining kinetic energy as it goes. And so energy is being put into the kinetic energy of that charge, which means it had to come out of somewhere else. So the potential energy, once again, has to have decreased by the same amount that the kinetic energy of our charge has increased. And so we have this relationship, once again, that the change in potential energy of our system is equal to the negative of the work done by the electric field. Now, obviously, these two potential energies are not the same kind of potential energy. This potential energy has to do with gravity, and this potential energy has to do with electric fields. And so let's label them for clarity. This is the change in gravitational potential energy, and on the right here we have the change in electric potential energy. This brings us to an important rule. When a gravitational force or an electrical force does positive work on a mass m naught or charge q naught, there is a corresponding decrease in the potential energy of the system. This is really just another way of stating that the total energy of a closed system is conserved. Unfortunately, there is one complication with electric potential energy that we've never had to worry about with gravitational potential energy. Consider again a region inside two oppositely charged parallel plates where the electric field is uniform inside. Where should we place a positive charge, Q naught, so that it has the highest amount of potential energy? If we place it right at the bottom near the negative charges, it's going to be pulled to the bottom, right? The negative charges here are going to attract the positive charge toward them, and the positive charges over here will repel this positive charge away from them. And so if we place this charge right at the bottom, it's stuck. It can't go anywhere. And so we can say that it doesn't have potential energy, or at least no potential energy that we can take out of the system with this contraption. On the other hand, if I place my charge up here, it's going to be pushed away, repelled from the positively charged plate up top, and attracted to the negatively charged plate at the bottom. It will experience a downwards force, and it will end up displacing downwards, which means that once again the electric force is doing positive work on our charge, and that means the potential energy must be decreasing, and that means we must have higher potential energy where we started than where we ended. In other words, our system has a greater potential energy when our positive charge is closer to the other positive charges, and or when it's far away from other negative charges. And you can remember that like this. When our positive charge is up here near the other positive charges, it's experiencing a force away from the positive charges, and those charges can push this away for a very great distance. And in fact, if this negative plate weren't even here, it could keep on being repelled away, and it would in fact never stop. So there's an infinite, or there's a very large displacement over which this charge can experience a force in the direction of its displacement if it starts out near the positive charges. Whereas if it started out over here, it's missing out on all this displacement that it could have experienced under the influence of the charge from these positives. On the other hand, if I ignore the top plate and I consider only the effect of these negative charges, if this positive charge starts far away, again, the negative charges can attract it, pull it downwards over a large displacement, which means there's a large amount of work to be done. If our charge starts out close to the negative plate, once again, we're missing out on this displacement that it could have had. And so when this charge is far away from negative charges, or close to positive charges, it will have a large amount of potential energy because the arrangement of charges is going to conspire to allow this object to experience a force in the direction of its motion for a greater displacement. We can already see how this is a little bit different from gravity, because with gravity we don't have these positive and negatives to consider. There's more potential energy when you're far away from another mass because there's a greater distance over which the masses can come together. But now we have to worry about the different effects of positive and negative charges. And this is where it gets even a little bit trickier. Let's consider replacing our test charge with a negative charge instead. If we leave this charge up here, well, it's going to be attracted to these positive charges right next to it and repelled by these negative charges far away, and it's not going to go anywhere. It's already as far as it can go. It's already right up against this positive plate. And so there's actually no work that can be done on it. It's stuck. So it has very little potential energy right now. On the other hand, if I move it all the way down here, it's going to be repelled by the negative plate on the bottom, and it's going to be attracted by the positive plate up top. So it will experience an upwards force, and it'll be displaced upwards all the way until it hits the other plate. And so we see here that when this negative charge starts out close to other negative charges and far away from positive charges, it actually has a great deal more potential energy because it has this greater displacement over which it can be forced. So we can add some more rules here, one of which is our system has greater potential energy when negative charges are close to other negative charges. We don't really need to add the fourth, which was that we have high potential energy when negative charges are far from positive charges, because that's already covered by the second rule, right? When positive charge is far away from negative charges, well, that implies that the negative charges are far away from the positive charges. So these three rules pretty much cover it. We will have higher potential energy when like charges start out near each other, or when opposite charges start out far away from each other. All right, so let's take a little bit of a tangent for a second. And I want to pose the question, what is the difference between an electric field and an electric force? Well, the field is something that's created by a lone charge. This field exists everywhere, though I've only drawn it in a small region, but it has a value and a direction at this point, and at this point, and at this point, and at this point, and here, and here, and here, and anywhere else you can point to. And even if you hover your finger a couple inches away from your screen, if this charge were actually there, there would be an electric field at that point as well, a magnitude and a direction. So this electric field is created by the presence of this single charge, and it has a value everywhere. And it doesn't depend at all on anything else. Even if there are other charges, this one charge Q naught creates its own electric field that has a magnitude of K times Q naught over R squared, and a direction that points away from the position of the charge. So then what's an electric force? Well, to talk about an electric force, I have to bring in another charge. If I just have one charge, there is no electric force. I need to bring in an additional charge, so let's do that. And let's specify that this blue charge is positive, just to keep things simple. The way I drew the original electric field here implies that Q naught is also positively charged, and we know that positively charged objects will both repel each other. If we look at the electric force specifically on the blue charge, we see that the force on it is equal to its own charge times the electric field that it's experiencing, that it's present in. The electric force tells me how these two charges will interact. The electric field created by Q naught tells me what it will do to any charge that I place in its field. So I chose to put a positive charge Q over here, but if I had put a negative charge, it would have experienced a force in the opposite direction. But I don't have to change this equation to show that. If Q is negative, then there's a negative sign here, and F and E therefore have to be in opposite directions. So the electric field created by Q naught tells me what force Q naught will apply to any other charge that I bring near it. We can see that mathematically by writing this equation that relates force and electric field a little bit differently. If we read this equation now, it tells us that the electric field in a particular region can be thought of as the amount of force that will be imparted per the amount of charge that I place there. In this particular example, there's not a lot of benefit to using this expression over Coulomb's law. Coulomb's law is just kq1 q2 over r squared, and this reduces to the same thing. Once I plug in the electric field of Q naught into E, I just get Coulomb's law. That's not always the case, though. For example, consider something like this. Let's say I want to find the force on a fifth charge, Q5. Well, one way I can do this is I can use Coulomb's law 4 times. I can use Coulomb's law for Q1 on Q5 and Q2 on Q5 and Q3 on Q5 and Q4 on Q5. Just like the work that we've done already, I could then break them all up into x and y components, and I can use trigonometry, and I can add them as vectors, and I can end up with a magnitude and a direction for the force on this charge. But what if I want to put a different charge here instead, after I've done all that work? Let's say I replace Q5 with Q6. Maybe it's the same sign, maybe it's the opposite sign, maybe it's bigger, maybe it's smaller. If I want to find the force on Q6, well, I have to do the same process all over again. Now, in this case, I can actually cheat a little bit. I can take the result that I had the first time, and I can simply replace Q5 with Q6 everywhere. So that's not so bad. However, let's say I've calculated the force over here, but now I've changed my mind, and it turns out I actually want to find the force over here. Well, now I have to start all over again. I can't use any part of my previous calculation to find what the force would be over here. I simply have to use Coulomb's law and start over from the beginning. Alternatively, what I could do is, before even worrying about Q6, I can do some math and I can find the electric field everywhere as a function of my x and y coordinates. So, for example, maybe I want to know, I can say, okay, well, what's the electric field over here? Well, I can calculate its magnitude and its direction, and I can do that over here, and I can do that over here, and I can do that over here. Now, if we wanted to do it with the tools that we've spoken about so far, that would be next to impossible. It would be really hard for us right now to do this. But this is a skill, for example, that you would learn how to do maybe if you take Physics C or if you continue to take physics in college. It's possible to simply compute a function that gives us the value, the magnitude and the direction of the electric field everywhere, wherever I look. I simply plug in the corresponding value of x and of y. If I have that, now my work is really easy. Let's say I've calculated my electric field and I decide, you know what, I'm going to place Q6 right there. Well, the electric force on Q6 is simply equal to Q6 times the electric field at this position. And since I already calculated the electric field as a function of position, I can simply plug in the x and y coordinates of this position into here and just multiply the result by Q6. And maybe then I change my mind and I decide, you know what, I want to place Q6 over there. Well, I can do the same thing. I can just find the force on Q6. It's equal to its charge times the electric field at this new position. And since I already have the electric field as a function of position, I just take that and I multiply it by Q6 and I'm done. So finding electric fields as that due to a configuration of sort of pre-existing charges, lets me do the work up front once, and it tells me everything I will ever need to know about any charge I can place anywhere. So if I want to place my charge here, or there, or there, or there, I simply take this function that I've already computed, and I multiply it by Q6 after plugging in the correct values of x and y. We have actually seen this before. For example, consider an elephant in a tree. When the branch inevitably breaks, the elephant is going to fall. Well, how do we know how fast the elephant is going to fall? We know that the gravitational force on the elephant is going to be equal to the elephant's mass times the acceleration due to gravity. But what's the acceleration due to gravity? It's simply the gravitational field. It tells us what is the direction and strength of the gravitational field at any particular place. So for example, right here, Earth's gravitational field points downwards and it has a magnitude of 9.81 meters per second squared. And as long as you're somewhere close to the surface of the Earth, that's going to be more or less constant. But that's really what we're doing. First, what we did was we found the gravitational field strength. That makes it easy to calculate the gravitational force on things caused by the Earth, because all I need to do is multiply g times the mass of the object. And so once I've found the field strength, it doesn't really matter what's causing it. Notice that we don't have to know the mass of the Earth in order to calculate the force of gravity on another object. If I know what my mass is, and I do a simple experiment to figure out what the value of g is, like you all did in the beginning of the year, then I can find this force, even if I don't know the mass of the Earth. So the field lets me figure out what's going on with forces, even if I don't really know all the details of what's creating the field in the first place. The field encodes all the information about Earth's gravity without me having to know all the details about the Earth. Likewise, if I'm talking about electric fields, the same thing is true. If I calculate or perhaps even just measure what the electric field is, then I don't need to know where all the charges that are creating that field are or how big they are, whether they're positive or negative. All that matters is that I happen to know what the field is right here. And as long as I know what the field is right here, then I can find the force on any arbitrary charge that I place here simply by multiplying Q times E. But what if it's not the force that I care about? What if what I really want to know is how much energy I'll have if I place a charge right over here? We haven't really learned how to find potential energy between 2-point charges, and we don't really need to for the purposes of this class, but it can be done. And one way that I could do this is I could find, well, what's the potential energy associated with these two charges with their values and the distance between them, and then I can add that to the energy associated with these two, and then the energy associated with these two, and then the energy associated with these two. But once again, what if I change my mind and I want to find the potential energy if I put my charge right there? Now I have to do it all over again. And if I decide, you know what, I don't want to know what's going to happen if I put it right there, once again, I have to do it all over again. So it would, again, be nice if I could find some property that depends only on where these charges are, that determines how much energy this charge will have if I place it in a certain position. I don't want to have to calculate the energy associated with this charge here caused by each of my 4 charges every time. I want to sort of clump together everything I know about these 4 charges first so that I can simply say, okay, well, if my charge is put here, the energy will simply be whatever that quantity was that I calculated times this charge. Now, once again, we've seen that with gravity. If I want to calculate the elephant's potential energy, well, I would figure out where have I decided to call my zero. Remember, the actual value of potential energy isn't really what matters. It's only differences in potential energy. And, usually we say that 0 is the ground. Why not? Well, in that case, I have to figure out, well, where is the elephant? The elephant is here, of course. The elephant has an x and a y coordinate. to calculate the elephant's potential energy, I want a function that lets me take the elephant's position and lets me take the properties of the elephant itself and just turn that into the potential energy. We already know how to do that. There is a quantity m, which depends only on the elephant. There is a quantity g, which is the gravitational field. And again, I don't know the details necessarily of what created it. We can measure g without knowing the mass or the size of the Earth, for example. And it also depends on the elephant's position. But what if I replace my elephant with a much smaller elephant? Clearly, there's much less potential energy in our system now because the elephant is smaller, and so the elephant has much smaller mass. If you look at this equation carefully, you'll notice that it depends on basically two things. One is the property, in this case, the mass of the object that I'm placing. And the other, g times y, tells us something about the field itself. It tells us what is the value of the field and where am I placing my elephant in the field. We can rewrite this as the potential energy divided by the mass. Note that in this equation, g is a scalar. It's the field strength. It's not the field vector. So the potential energy per mass depends only on this quantity that I've already computed, and that applies everywhere. What this tells me is, what if I want to know the potential energy of my system if I place an elephant right over here? Well, I know that the potential energy divided by the mass, whatever I'm going to place, is simply equal to this value, g times y. And so g times y is sort of like the potential to have potential energy. It tells me how much potential energy will I have per kilogram of mass that I place at position y, or height y. This potential to have potential energy, the potential energy per unit mass, is given a really unfortunate name. We call it potential. I am so sorry. Now, there are different kinds of potential energy, right? We have gravitational potential energy, for example, but we also have electric potential energy, as we discussed earlier. And so we have different kinds of potential, too. There's gravitational potential, which is what we just discussed. And again, what this quantity really means is if I were to place some kind of object in some place, all I need to know is its mass and the strength of the gravitational field that I'm working in, and how high I'm going to put this object. G times y is a measure of the potential for something to have potential energy. If I place 1 kilogram of mass there, I'll have 1 kilogram times the gravitational potential at that position. If I want to put a 3 kilogram object there, I would have 3 times that potential energy. And this quantity is useful because, once again, I don't need to know anything about the thing creating the gravitational field. I just need to know the field. And in cases where the sources of a field are complicated, this is a really big help. So let's talk notation for a second. So how do we represent this mathematically? Well, the symbol for potential is the letter V. If we're talking about gravitational potential, I would write this as V with a subscript G. We can talk about the units of our gravitational potential. It's the units of G, which is acceleration, times the units of Y, which is distance, for overall units of meters squared over seconds squared. The last thing we need to discuss then is this concept of potential in the context of electric fields. If gravitational potential is the gravitational potential energy per mass, then by analogy, we can write the electric potential as the electric potential energy per charge. To provide a little bit of context for this very abstract concept, let's again consider two charged parallel plates with an approximately uniform electric field between them. And let's talk about this potential thing. So the potential is a lot like a field. It doesn't depend on anything other than the charges that created it, right? It's the potential energy per unit charge that I could put here. This makes it useful for the same reason that fields are useful, but the potential is actually often a lot easier to work with. And the reason for that is the same reason why energy is often a lot easier to work with than forces. And that's because forces are vectors and energy is a scalar. And so with electric potential, it's just a number. I don't have to worry about directions or any crazy thing like that. It's just a number, and it tells me the potential for my system to have potential energy if I were to put some amount of charge Q in any arbitrary place. So let's consider this place right here. What might the value of potential be? If you think back to one of our earlier examples, we established that if I have a positive charge near other positive charges and far away from negative charges, the potential energy would be large because this positive charge would be pushed to the right. It would undergo a large displacement while experiencing a force in the same direction, and so the field would do positive work on it, and so on. So there must be a large value of potential energy for a positive charge over here. Well, if there's a large value of potential energy at this point, then the value of the potential should be large because it's the potential energy per unit charge. So for example, if I imagine putting a 1 coulomb charge here, it would have a certain large value of potential energy, and the potential would simply be that value divided by 1 coulomb. Or, working backwards, if I somehow have already measured or calculated the value of the potential at point A, then I could find the potential energy at point A if I place some charge Q naught at that value. That gives us something to consider though, because if the charge that we place there is greater than 0, then our potential energy of that charge at point A is going to be a positive value times the amount of charge times the value of the electric potential. And so we get a positive potential energy. On the other hand, if the charge that I place there has a negative value, then the potential energy at position A is equal to a negative amount of charge times the large value of electric potential. And so we can see that this one value of potential gives us exactly what we want to happen. If I place a positive charge close to these positive charges, I get a large potential energy. On the other hand, if I put a negative charge close to these positive charges, which we established means we have very little potential energy because this negative charge placed here has a very small displacement over which to have work done on it, it gives us a very small value of potential energy. In fact, it gives us a negative amount of potential energy. So now I can talk about the potential energy that my system will have, whether or not I place a positive charge or a negative charge, in terms of a single value, which is what we call the electric potential. We can do the same thing over on the other side. If I were to place a positive charge at point B, then I would expect it to have a low potential energy. And that means that the potential should be small. So VB should be low. And the potential energy of a charge placed at point B would be equal to the charge itself times the electric potential at point B. And again, we can write out what this will give us if the charge is positive or negative. And this actually gives us some useful information, because if you look at this, we see that if the charge is positive, if I place a positive charge here, I get plus Q times VB. But if a positive charge is over here, it should have a low amount of potential energy. Here I have a positive number times VB. Well, this is a small number, and I have a positive number times it. So, okay, that's small. But if I look at the second row, if I place a negative charge here, I have a negative charge times a low potential. Well, that gives me a negative number times a small value. You might think, well, but I should have a large amount of potential energy, not just a small negative amount of potential energy. First of all, remember, negative, positive, it doesn't really matter. The only thing that matters are differences in potential energy. But either way, if VB is a small positive number, then this is a small positive number, which means we have a small positive amount of potential energy. And if VB is a small positive number, then this is a small negative value. It doesn't make sense, though, for the positive charge to have more potential energy at point B than a negative charge would have. And so what this is really telling us is that VB itself is less than 0. Now this works, because if VB is a negative number, now my potential energy is negative. So over here, at point A, I have a positive value of potential energy for our positive charge. And at point B, I have a negative value, which means this value is certainly much smaller than this value was. On the other hand, over here, if VB is negative, then a negative charge times a negative potential gives us a positive quantity. And so we have a positive amount of potential energy. And so at point B, our positive charge has negative potential energy because VB is negative, and our negative charge has positive potential energy because it's a product of two negative numbers. And so it works out as long as this is true. And so this gets us to a quick rule, and that rule, or these two rules, sort of, are that electric potential is positive near positive charges, and it's negative near negative charges. And it turns out that the electric potential created by a point charge is given by the equation V is equal to KQ over R. We're not going to derive this. In fact, we're not even really going to use it, but it shows us that if you have a positive value of charge, then the value of the potential will be positive. It will create a positive potential. On the other hand, if Q is negative, then the value of V will be negative everywhere. It also shows us that as you get closer and closer to the charge, the magnitude of the potential gets bigger. And so we can graph these to get a better look, and it looks something like this. So the closer you get to a positive charge, the higher the value of potential. The farther away you get from a point charge, the lower the value of potential, and it approaches 0 as you get infinitely far away. It's the opposite for a negative charge. When you get really, well, not quite the opposite. If you get really, really close to it, the potential approaches negative infinity. But once again, when you get really far away, the potential approaches 0. I just realized I forgot to talk about the units of potential, of electric potential. So let's just do that now. So we know that the electric potential is equal to electric potential energy divided by charge. Well, that means that the units of the electric potential are the units of potential energy, which are joules, divided by the units of charge, which are coulombs. You'll note that these units are different from the units of the gravitational potential. That's because gravitational potential is potential energy per mass, whereas electric potential is potential energy per charge. So they have different units because they mean different things. One tells us something about gravitational fields, the other tells us about electric fields. The units of joules per coulomb are often given another name. They're often called volts. And just because this isn't confusing enough yet, right? We have potential energy and we have potential, and potential is symbolized by the letter V, and so is the unit for it. A volt is symbolized by a capital V. So this might seem like, oh, who the hell came up with this? Whoever it was should never have been allowed to be in charge of anything, and that very well might be true. But in the end, it isn't really confusing because there's never really ambiguity about whether we're talking about the variable or the unit. It will always be clear which one it is that we're talking about. While we're on the topic of units, this actually gives rise to a new unit of energy that is used when talking about electrostatics and circuits, which is our next unit. So if we rewrite this expression, which is that the potential energy of a system is equal to the charge that we place times the value of the potential at that position. The units of charge are coulombs, and the units of potential is a volt. Now, a coulomb is actually an enormous amount of charge in practice. It's almost unheard of for an object to have a coulomb of charge. Usually we talk about microcoulombs, nanocoulombs. So a coulomb is a very, very, very big unit of charge. And when we're talking about electric forces, we're often talking about really tiny things like electrons and protons. And electrons and protons have one elementary charge, right, which is way smaller than a coulomb. And so this leads to the unit that we call an electron volt. And it is equal to 1 elementary charge times a volt. And since 1 elementary charge is 1.6 times 10 to the negative 19 coulombs, we can rewrite this, an electron volt, in terms of joules by using the fact that a coulomb times a volt is equal to a joule. And so an electron volt is a very, very small amount of energy, but it's actually a very reasonable amount of energy for an electron or a proton or any other of these really small particles. We're almost done now. The last thing I want to do is just to provide some context, go over some examples of how we actually go about using electric potential in practice. So because the value of potential energy is actually not so important, but the difference tends to matter more, the same is true for the electric potential. We usually don't really care about the value of the potential at A or at B, but rather the change in potential from one to the other. And so we call that change in potential difference from one to the other, in this case, for example, the difference in potential from A to B is equal to the potential at B minus the potential at A, right? Because it's always a change is final minus initial. And we call this the potential difference. We can use this to calculate changes in potential energy. So for example, if you imagine placing a charge at point A, and we want to know how is its potential energy going to change if it moves from A to B, we can relate that to the potential difference between points A and B. For example, if the charge we're talking about is an electron, and the potential difference across points A and B is 1 volt, I actually have to be quite careful, because if you think about it, A has to be at a higher value of potential than B, right? Because A is near the positive charges and B is near the negative charges. And I'm going from A to B. So my potential is going from a high value to a low value. So the potential difference from A to B is the low value of B minus the high value of A. And so I have a negative sign because I'm losing potential as I go from A to B. I'm going from a high value to a low value, and so the change is negative. Calculating the change in energy at this point is straightforward, and we get 1 electron volt of energy. So this was a nice simple example. Note that in this case, if I put an electron at point A, it would never go to point B on its own, right? The electron is going to be attracted to these positive charges and repelled away from these negative charges. So what does this even mean? Well, it means how much energy would I have to put into the system to move the electron from A to B? This is kind of like lifting a book up off of a table. You have to put energy in to increase the potential energy of the system. So you have to do work on this system. So let's do this again, but this time let's talk about the change in potential energy of our system as our electron goes from B to A. This time we're calculating delta PE, but not from A to B, but from B to A. The charge of the electron hasn't changed at all, but this time we're going from the low potential side to the high potential side. So this time delta V is going to be positive. And so we get negative 1 elementary charge times positive 1 volt. And so we get negative 1 electron volt. And this time, the potential energy of our system has decreased, and that means the electric field has done positive work on our charge. It's used up some of the potential energy stored in the field in order to accelerate the electron from point B as it gets pushed away from the negative charges and attracted towards the positive charges. So what I'd like you to do right now is using the mass of the electron, which is 9.1 times 10 to the negative 31 kilograms. I'd like you to pause the video, and I want you to use conservation of energy to determine how fast the electron will be moving when it reaches point A, after starting at rest from point B. All right, so hopefully you are finished, and let's just quickly go through it. Conservation of energy tells us that the change in potential energy is equal to the negative of the change in kinetic energy. In other words, if the potential energy of our system went down, the kinetic energy of something in the system had to have gone up. Plugging in the equation for kinetic energy using the mass of the electron and the change in potential energy that we calculated, you should find that the result is 593,000 meters per second. So as you can see, it doesn't take a whole lot of energy to make an electron go really fast, because electrons have very, very little mass. Also note that just like energy, it doesn't matter what happens in between. The change in potential energy depends only on the difference, on the potential difference from where we begin to where we end. What happens in the middle is completely irrelevant. We only care about the beginning and the ending. And so this is another way in which potential is a useful concept, because if I have an electric field that's really complicated and the field is changing from one point to another in a complicated way, it's going to be really hard for me to use forces to figure out how what the particle is going to be doing on the other side. But with electric potential, it really only matters what is A and what is B, and I don't care about the middle. So just like the potential has all the benefits of working with energy, because it really is the same kind of concept of energy. It is, in fact, the potential for having potential energy. One more example that we can do is if we know, for example, like a function of electric potential, how can I figure out how charges placed in that region will behave? So consider this function, for example. The x-axis represents position, and the vertical axis represents the value of the electric potential at that position. So at this position right here, the electric potential has a positive value. And if I keep moving to the right, the value of the potential keeps increasing. What would happen if I place a charge right here, a positive charge? If we knew which direction the field pointed, this would be easy. The positive charge would move in the same direction as the field points. But I didn't give you the field, I gave you the electric potential in this region. We can still figure it out because we know that positive potential is created by positive charges, and negative potential is created by negative charges. And so anywhere the potential is positive, it means there must be other positive charges in that region. It's important to note that this red curve represents the electric potential created by other charges, and I'm placing this blue charge in the midst of them. I want to know their effect on this charge. So in principle, this charge creates its own electric potential, but charges cannot exert forces on themselves. So as long as we're talking about this charge, we only care about the potential created by other things. Now, on the right-hand side, I have a positive potential. That means there must be positive charges over here on the right. And on the left, I have negative potential. That means I must have negative charges over here on the left. Well, positive charges are attracted to negative charges and repelled by positive charges. So this positive charge will experience a force to the left. It's important to distinguish the fact that it will experience a force to the left with the fact that it could move to the left, because it might not move to the left. It might already be going to the right so fast that it's only being slowed down. So this graph doesn't tell us what the electron or what the positron or what the particle is currently doing. It merely tells us how is it accelerating, what force is it experiencing. This gives us a really useful rule, and that is that positive charges will experience a force in the direction towards lower potential. And since low potential is created by negative charges, or negative potential is created by negative charges, positive potential is created by positive charges, this is essentially an alternate way of saying that positive charges are repelled by other positive charges and attracted by negative charges. Now let's do the same thing, except let's place a negative charge in the same place. Again, since the potential is positive along the positive x-axis, it means there's got to be a concentration of positive charges somewhere over here. Likewise, the value of the potential is negative on the negative x-axis, which means there's got to be a concentration of negative charges somewhere over here. And since negative charges are attracted to positive charges and repelled by negative charges, our negative charge is going to experience a force to the right. This gives us a corollary to that rule, which is just that negative charges are forced from low to high potential. Bear in mind that since the change in potential energy of a charge is equal to its charge times its change in potential, in the case of the positive charges, they're being pushed from high potential to low potential. So this implies that the potential difference is negative. And if the delta V is negative and Q is positive, that means our system is losing potential energy. It's transitioning to a state of lower energy. If we do the same analysis for the negative charge, well, it is being forced from low to high potential, which means delta V is greater than 0. But the charge itself is negative, and that implies that the potential energy is going down because delta PE is negative, because a negative charge times a positive potential difference is equal to a negative value, and a negative change means it is decreasing. And so in both cases, we find whether I place a positive or a negative charge in a certain position, it will be pushed in a direction to minimize the potential energy of the system. This leads to this is related to a really fundamental rule in physics, which is that pretty much any system will tend towards a configuration of lower potential energy. This is the basis for a lot of the rules that you learned in chemistry, for example. It determines what molecules are stable and what molecules aren't stable. If a molecule can break up into pieces whose result is lower potential energy, then it will almost always end up doing that, at least after a certain amount of time. One kind of heuristic way of thinking about what direction positive and negative charges will go is that positive charges will kind of roll down a curve of electric potential because they're pushed from high to low. So if they start out at a certain place, they will always end up experiencing a force pushing them downwards. That's kind of like how masses behave in gravity, right? Gravity always pushes things downhill. Negative charges do the reverse. If I place a negative charge at a negative potential, it will experience a force towards higher potential, and so negative charges can be thought of as sort of sliding or rolling uphill along the curve of potential. Now remember, in this example, the charges are really moving along a line. They are not moving along this curve. This curve is a function that represents the value of potential at a certain position. These charges are moving left and right. So a positive charge right here will move or accelerate to the left, and a negative charge, regardless of where it is in this particular graph, will accelerate to the right. That's it for today. And I apologize again that this is fairly long, but you have a decent amount of time to get through this one. And next time we will actually start circuits, and understanding the concept of potential is really important for understanding circuits.